Pretty important lesson today, wrapping up chapter 2, and we're going to begin the year. This begins a process for us of identifying what are known as parent functions. And by the time we're finished with Algebra 2, you're going to have a small little library of parent functions that you should be able to recognize very quickly, draw very easily. They're going to be your friends as you go into higher level math, those of you who are headed to pre-calculus and beyond. So I want to start with what 3 of those parent functions look like, and then what do we mean by transformations of these functions. So let's just start by identifying some terms. There are really 3 different types of transformations. One of them is known as a translation, and I've given you part of the definition here. When we take a figure or a graph and we slide it, or sometimes you'll see the word transfer it from one position to another. Or maybe you think of one location to another. But in the process of relocating it, it will not be turned or rotated. It maintains its exact shape. It's just going to be moved to a new position. And then another type of transformation is known as a reflection. And when we see the word reflection, we're thinking flipping. We're thinking flipping a figure in a line. And for us, that line is either going to be the x-axis, flipping it vertically, or the y-axis when we flip it horizontally. And I'll tell you in just a little bit how you'll know which is which one to do. And then we come to our final transformation, and it's known as a dilation. And this is where we change the size of a figure, but not the original shape. What I mean by that is, if it started off as a V, it's going to still be a V. It's just that it might be a really wide V or a skinny V. And the same would be true for the U shape, the parabola. It's still going to be a parabola, but a dilation affects it so that it will either be wider or skinnier. And you'll see the effect of those. We put all these together, and we refer to this as a group of transformations. Transformations. Squeeze that in. So when you see the word transformations, you're thinking one of these 3. We could do all 3 to a shape, but I want you to know what these are referring to. And then we're just going to take them in this lesson. We're going to take these one at a time, and we're going to look at how to perform these on what are known as parent functions. So we're going to start with the real basic parent function. I told you earlier, you're going to learn 3 parent functions. Think of these as the starting point, the originator. And it's from this parent that we can come up with other, if you want to think of children graphs, but they all start with one of these parents. And the first parent we're going to look at is y equals x. This has come up a few times so far throughout the year. The graph of y equals x looks like this. If you think y equals mx plus b, well, there is no b showing, so b is understood to be 0. So we've got to cross at y equals 0, or the origin. The number in front of x always indicates the slope, and there is no visible number. It's understood to be 1. So from our y-intercept of 0, we count a slope of positive 1. And this is the graph of y equals x. It goes through the origin, slope of 1, positive, and the line y equals x is important for other reasons that we'll talk about later, but it is one of our parent functions that I want you to be very familiar with going forward. Okay, well, a translation, remember, it's like taking the parent and shifting it or sliding it to a new spot. So when you see this, this represents a translation of the parent. You can see y equals x in this equation. It's like saying, let's take the parent y equals x, and by adding this number called k, it's a vertical shift of whatever k is upward. So let me give you an example. In red, I'm going to write the equation y equals x plus 3. Well, what that says in translation language is, take the original blue parent function, y equals x, and all of the points on it, just move those points up 3 places, and then draw the result. So this would be called a vertical translation of the parent, y equals x. It's a shift. Over here, notice that in this case, we've still got the same parent, starting off with the same parent, but subtracting some number called k has the effect of lowering or dropping or shifting downward, taking the original blue and moving it down whatever k is. So let's just do a quick little example. The parent is, you can see it, y equals x. And that's like saying move the parent function down 2 places. So the parent started at the origin, and every point on the parent gets shifted 2 places down. Okay, so the takeaway before we move on, I want you to know what the parent y equals x looks like. You should, by the time we're finished with Algebra 2, you'll probably draw it in your sleep along with the other parents. Pretty simple. And then how do we translate or shift based on what we're told, what k is? If k is positive, we're shifting up. If k is negative, we're taking the parent y equals x and we're shifting down. All right, moving right along. Our next parent is the absolute value function. Y equals the absolute value of x. We already know from previous lessons that the absolute value function has to produce a V shape. Has to. So the absolute value parent function looks like this. It has vertex at the origin. It has a slope of +1 and -1 because it's got to have 2 lines in order to make a V. So our absolute value parent looks like this. Okay, well let's talk about how we shift or translate this absolute value parent based on these numbers that we're identifying as k in my first example, and then we'll talk about h over here in this other example. Let's start with this k. Notice that k is some number that I'm showing addition, but it could be adding a negative, which is the same thing as subtracting. But the point here, the big takeaway is, notice that k is outside of the absolute value. That is crucial, because anything added or subtracted outside of absolute value always indicates a vertical shift. Vertical meaning up and down, up or down. Okay, I'll say it one more time because it's important. When I'm adding or subtracting a number, in this case it's identified as k, outside of the absolute value walls, it tells me that I'm going to start with this parent and I'm going to shift it vertically, whatever k is. So let me give you an example. Here is my absolute value parent, and I'm going to put in -3. Well, this says to take the parent function, which looks like this, and shift it down 3 places. All the points on the parent get moved or transferred 3 places down. And I don't normally have double arrows, but just to save time, I think you understand that really should be arrows here on the other end at that point. All right, I'm going to do another example just to illustrate this vertical shift, this vertical move. I'll do this one in green. And since you don't have colors, you might just want to label or graphs. We'll call this one y equals epsilon of x minus 3. And then in green, I'm going to do another one. Here's the parent again, but outside of it, I'm going to put plus 4. Well, two things. I'm adding 4 outside of the absolute value wall, so that tells me it's got to be a vertical shift. And since it's positive 4, I'm taking this original parent and I'm moving it 4 places upward. All the points on the parent get shifted 4 places up. This is the effect of translating the parent function y equals absolute value of x vertically. Okay, questions so far? All right, let's jump over here, and you notice that now I've got this variable h that stands for a number, and it's inside the absolute value. Outside, adding or subtracting always indicates vertical movement. Inside the absolute value always indicates horizontal movement. But you got to really be careful. Horizontal can be tricky. I'll show you why. Okay? H represents a number that tells me whether I'm going to move left or right and how many. Okay? I'm going to write a function that represents a horizontal translation, and I'm going to write it right above this. We'll call this the definition of horizontal translation. If you compare what I wrote in blue to what was already given to you as the definition, y equals, absolute, x minus, h is what? 2. Do you see that? Okay, not negative 2. H is literally 2, right? 2 is a positive number, right? So if I'm thinking left or right movement, and I have a positive number, it makes sense that I'm going to be moving to the right. Agree? So this represents a translation of the original parent 2 places to the right. Now it's tricky for a lot of people because they see that minus sign and their first thought is, well, it's got to be left. Well, it's all about what h is. Whatever h is, h being positive says go to the right that number. Now I'm going to give you an example of what it looks like when you go to the left. Colors. Okay, are you with me so far? All right, right below this, let me just do this in red. I'm going to do another equation that represents the translation. This time I'm going to do plus 3. Y equals the absolute value of x plus 3. Well, if you compare what I just wrote to the original definition of the translation, what must h be in order to make this become plus? Doesn't it have to be negative? Because isn't subtracting a negative the same thing as addition? So remember, when you're dealing with horizontal translations, you've got to think about what h is. And in this case, h has to be negative 3. And negative means I've got to move to the left 3 places. So I'm going to take the parent, and all the points on the parent, I'm going to shift 3 places left. So horizontal shifts or translations, you really have to be careful. It looks opposite of the way it really acts, if you think about it. Because it's all about what h is. Don't look at the sign and just have a reaction that's got to be left if it's minus. So you think about what h is, and that'll tell you whether to move left or right. Yeah?
So if it's a plus,
yeah, plus really means you're going to the left, because h would have to be a negative number to turn this into plus. So again, it's all about h. It's not really what the sign is in front of the number. Okay, good question. Anyone else? All right, so let's put horizontal and vertical together. starting with the parent y equals the absolute value of x, and this would be called a diagonal shift when we combine these two moves in one function. So let me give you an example. Y equals the absolute value of x plus 5 minus 3. So somebody want to raise your hand and tell me, let's start with the horizontal shift. Horizontal means left or right. Am I going left or right? And how many, Landon?
Left 5.
Left 5, very good. So I'm going to start like the parent starts at the origin, and I'm going to go left 5, but I'm not going to make a dot there. I'm just going to rest. Okay? And then this minus 3, outside of the absolute value, always indicates a vertical shift, and the great thing about vertical is it's not tricky. Plus means up, minus means down. So Josh, I'm going to go left 5, and then from there I'm going to go down 3. And all the points from the original parent do this same thing. They go left 5, and they go down 3, and that's the result. Any questions so far? Now the great thing about these transformation principles that we're going over, like I said, we're going to learn 3 parents today. We've already learned 2. We just got 1 more. We're going to get somewhere in the neighborhood of 8 or 9. I can't remember which, but all of these rules apply. Every time we come up with a new parent, the transformation rules still apply the same way. So once you get this down, you'll be able to transition to the other parents, how they're transformed really pretty easily. You're going to see that right away when we get to this parent. Okay, here's our third parent of the day, the quadratic function y equals x squared. It's got to be a U shape. So here's what the parent looks like. I've got this activity called algebraics, where we treat the floor like graph paper, and we actually do these using our arms. So when I come in and we do algebraics and I say show me y equals x squared, you're going to show me the U shape with your arms. When I say show me y equals the absolute value of x, you're going to show me the V shape with your arms. And then when I include translations, you're going to walk along the tile, up, down, left, or right. Okay, it just kind of helps us get these transformation rules down. Well, here's y equals x squared. Vertex at the origin, just like the V. If I input 1, I get output 1. If I input negative 1, I get output 1. There's symmetry with the y-axis. If I input 2, I get output 4. If I input negative 2, I get output 4. Remember, there's symmetry with the y-axis, so if you get a point on the right side of the y-axis, there's a matching point on the other side. And so here's a rough sketch of the parent, y equals x squared. So those same rules, principles that we dealt with translating the absolute value parent, they're still in use. Outside of any grouping symbols, adding or subtracting means vertical shift. So let's just do an example. Y equals x squared plus 4. Well, the plus 4 is not in any kind of grouping symbols, no parentheses, so it's got to be a vertical shift. Vertical is great because plus means up, minus means down. So sometimes the book is going to say, what is the parent function? And describe the translation of the parent. Well, the parent function, you can see it, is y equals x squared. The translation is that we're shifting y equals x squared up 4 places. So all of the points on the parent go up 4 from the original. So the original had 2, 4, so I'll start there and go up 4 more. 1, 2, 3, 4. And then matched up over here. So this is a vertical translation. adding 4, and the 4 is not inside any parentheses. Outside, vertical. Outside, vertical. Okay? Inside, horizontal. So let's just do an example of that horizontal shift. Based on what you learned earlier, off an equal sign. This is a translation of the original parent, y equals x squared, but which way am I going? Left or right? I'm going left 4 places. So it's like taking this original blue and sliding it 4 places to the left. And then draw the original, showing that all the points have been moved. Any questions so far? You guys are doing a great job listening. Any questions? Is this pretty simple? Have you seen this before? Anybody? All right, well, let's put them together and see what you can do with this. Kate, I've got 2 movements here. There's a horizontal shift and there's a vertical shift. Can you tell me, first of all, let's start with the horizontal. Am I going left or right? 1.
You're going right one.
I'm going right 1. H is 1. And then from there, I'm going up or down?
Down.
Down 5. And that's the vertex of this translated parent. And then you just make all the points do the same thing. Every point on the parent got shifted 1 to the right and 5 down. And this represents the translation of the parent. Translation again just means shift, transfer. Any questions? We are leaving translations, and now let's talk about reflections. Remember, there's really 3 ways to transform a graph. Translation is only one of the ways. A reflection is a flip. And we're either going to be flipping a graph over the x-axis, which would be like a vertical flip, or the y-axis. Those are our 2 choices. And I'll show you how you know. It's pretty easy. If I don't have a minus sign, notice how I've included the minus sign in front of x squared. We haven't dealt with that yet. The minus sign that is not, don't do this to your notes. Let me just show you a counterexample. A minus sign that is not included in parentheses. Okay? Notice how I just changed it to where minus is in parentheses, but ours is not. So again, think outside. When we were dealing with numbers before that were outside, and we were talking about a shift, was that a vertical or a horizontal shift? When the number was outside. Vertical or horizontal? Vertical, okay? Well, you can think the same thing when it comes to the flip. When the minus sign is not inside parentheses, or in other words, it's outside any kind of grouping symbol, that's got to be a vertical flip. It's got to reflect. Let's first of all fill in the blank. This is the parent, y equals x squared. You should be able to recognize the original parent, and there's only 3 choices today for tonight's homework. It's either got to be y equals x, y equals the absolute value of x, or y equals x squared. Those are the only 3 parents you're dealing with in this lesson. So we've identified the parent, and since it's not involved inside parentheses, that means I've got to have a vertical flip, and that is going to be over the x-axis. So I'm going to draw the parent. You don't have to draw the parent when you do your homework. You just have to draw whatever it is that they've given you. But I want you to see the parent and the reflection together. So remember, let's just go ahead and draw y equals x squared. Here's the parent. Let's label it for you. The blue is our original parent, y equals x squared. By putting this minus in front and showing that it's a reflection over the x-axis, it's literally picking this blue parabola up, flipping it over, that's what reflection means, and setting it down on the other side of the x-axis. So the red is, missed that one. The red represents this, the negative x squared. So the big takeaway between this slide and the next, how do you know if you're going to be reflecting over the x-axis versus how do you know you're going to be reflecting over the y-axis? Well, again, let's move inside. Going back to translation, remember we said when we're adding or subtracting, we know we're going to have a horizontal shift. We just have to be careful that we go the right direction, but we know it's got to be horizontal. Well, that same idea is true when it comes to the flipping. I've now moved the minus sign inside parentheses, so I've got to have a horizontal flip. So that means it's got to be which axis if it flips over this way, x or y. We've done x already, it goes this way. We're flipping over x vertically, so the only other choice is it's got to reflect over the y-axis. So this is that same parent, y equals x squared, but when I've got the negative sign inside parentheses like this, now it's going to reflect over the y-axis. So let's see what it looks like. Let's do the parent real fast. You go ahead and do the parent on your graph paper. Hopefully you'll get real fast, and we just need these 5 points generally to represent the parent. Make your U shape. Okay, so let's do some visual thinking here. If I were to take this blue parabola, pick it up, and flip it over, set it back down so that it is reflected over the y-axis, what do I have? It's the same thing. All we're saying is we have symmetry, basically, with the y-axis, which is true of all parabolas. Well, if you need some ordered pairs to prove it, let's just do, for example, Josh, what if I input -1 for x? What's the output? Well, I just want you to, right or left would be adding or subtracting. I'm just doing an input right now. I think you're thinking translation. I'm not adding or subtracting, I'm just literally plugging a number in for x and then trying to get an output. Can you tell me what the output would be? Well, yeah, isn't that true? If I input -1, I get +1. Isn't that what I got with the original? So there's really no difference when I'm taking this parabola and reflecting over the y-axis. It's really just like a parent. Just pick it up and flip it. That's what reflect means. Okay, so the big takeaway. Minus sign in front of our function that is not in parentheses, that's always going to reflect over x. Always. When I do this, I've now changed it so that it reflects over y. Okay, no parentheses, or, let me give you another example. Am I reflecting now over x or over y with this example? I'm reflecting over x because the minus sign is outside. When I move it inside, I am now reflecting over y. Okay, so that's translations. I provided a slide for you that really there's nothing to write down, but as you're doing the assignment tonight, this might come in handy. As you're doing reflections, these are some important things to remember. These all represent reflections in x. That's flipping vertically. When we move the negative inside, these all reflect or represent reflections in y, flipping horizontal. Okay, questions so far? All right, we got one type of transformation to go, and this is a dilation. Again, dilation changes the size, but not the shape. Think skinny or fat. We're going to take the parent and we're either going to make it skinnier or fatter when we dilate. Okay, let's see what the effect of multiplying by 2 does. Well, first of all, let's draw the parent. So you can go ahead and get ahead of me. So far, you've done this parent so many times, it's going to be really easy for you to do it. Here's y equals x squared. Let's do that. Okay, now let's think of some inputs, outputs. Kate, input 0 to this, what's the output? 0. Okay, I'll do the dilation in red. Okay, Kyle, input 1, output 2. Input 1, output 2. And I got a matching point over here. Trent, input 2, output 3. Let's see, 2 squared.
4.
2 squared is 4, and then 4 times 2?
8.
Okay, if I input 2, output 8. And there's not a huge difference, but there's enough to where you can see that the red is a little bit skinnier. So here's the bottom line. Whenever I put a number in front of x squared, or it could be the absolute value of x, it's the same thing, and that number is greater than 1, it has the effect of what we call, well, first of all, this is the parent function, y equals x squared. Hopefully you saw that. When there's a number in front of x squared, or the absolute value of x, it really doesn't matter, and it's greater than 1, we call this vertical stretch. Or to stay in context here, I'm going to say the function is stretched vertically. And that's just another way of saying that the original parent is getting skinny. If we could literally, if this were pliable, and we could grab these arrows and pull upward on them, and this was anchored here at the origin, and we just grabbed and pulled upward, you can kind of think of how if this was a rubber band, we would kind of stretch it and it would get skinny the more we pulled it up. And that's kind of the same idea if you can visualize that. The effect of a number in front of x squared, or the absolute value of x that's bigger than 1, always has this. And the bigger the number, the skinnier the parabola. If this were y equals 16x squared, that's going to be a really, really skinny parabola. And we call it vertical stretch. Okay? Now let's look at the opposite of vertical stretch. Okay? Go ahead and draw your parent again real fast. This is the parent y equals x squared. I'll give you about 20 seconds to get your parent drawn. Okay, you guys are doing great. So here's the parent. Now, this time in front of x squared, I have a fraction. And this would apply also to if this were absolute value, the absolute value parent. All right, so let's do some inputs, outputs. Micah, if I input 0, I get 0. Jackson, let's go with 2. Input 2. Okay, input 2, output 2. 2 squared is 4, 4 times a half is 2. And I've got symmetry on both sides of the y-axis. Jake, if I input 4, 8, 16 times a half. Okay, so the blue represents the dilation. Kind of too far over. The blue represents the dilation of the parent. And you can see the effect when our number that we're multiplying by is a fraction between 0 and 1. Previous example, it was a number greater than 1. So this is not vertical stretch, it's just the opposite. This is called vertical compression. Or to stay in context with my slide, I'm going to say that this is the parent compressed vertically. And that's just another way of saying it's getting fatter. If we were able to put pressure downward on this parent, pushing downward from the top, the force would probably cause it to widen as we got closer to the x-axis. That's another way of thinking of compression, pushing down. And that always happens when this number in front of x squared or the absolute value of x is a fraction between 0 and 1. Okay, so again, this is just a recap of everything I've said. I just gave this to you, so as you're doing your homework, you might want to refer back to this slide. Let's do some examples. I'm going to just save a little bit of time and jump over to these. Let's see if we can get these. And I'll get some help from you. The directions here say describe the translation in each function as it relates to its parent, and then graph. Okay? Well, number one, I'll just get us started. This is the parent y equals x squared. And it's a translation, it's shifting 3 units up. Shifted. Okay, and so here's the graph of this. If you have to draw the parents, some people like to draw the parents and then actually see how it moves left, right, up, or down. I'm not going to require that, but if it helps, do whatever it takes. But here's your final answer. This is the parent U that did have the vertex at the origin, but all the points on that U are going 3 places upward. And there's my answer. Okay, anybody want to try number 2? What's the parent on number 2? Samantha, what's the parent being translated? Okay, so this is y equals the absolute value of x, and then what's the translation? Are we going up, down, left, or right? Well, outside of absolute value means up or down. Down 5. Okay, so this is the original parent, that's the V at the origin, but we're going to shift it 5 places down. Okay, number 3. August, what's the parent on number 3?
Y equals x minus.
Well, the parent, your answer will be either y equals x, y equals absolute value of x, or y equals x squared.
Y equals x.
Try again.
Y equals x squared.
There you go. Okay, there's the parent. And now the shift, that's another word for translation. Is it going to be left, right, up, or down, August? Right. 8. Very good. We're going to take the original parent, which had vertex at the origin, and we're going to move all the points on the parent 8 places to the right. It's going to be way off to the side. Okay, BJ, number 4, what's the parent?
Y equals absolute value of x.
Good. And BJ, what's the translation? Okay, 2 to the left. So the original parent had vertex at the origin, and we're going to move all the points on the parent 2 to the left. And so it looks something like, man, I'm struggling, can't connect the dots real well. That's what I have to do. Good job. Any questions so far? Okay, now let's talk about reflections. What's the parent here, Campbell?
White was X, right?
Okay, and how is it reflected? Over X or over Y? Okay, it's going to be reflected over X, and we've already looked at what that looks like earlier in your notes. It's the original parent that looks like this. Pick it up and flip it over the X-axis, and it just opens down. What about number 6? What's the parent here, Jackson? Well, the parent, when you answer the question, what is the parent, you got 3 choices. Y equals X, Y equals the absolute value of X, or Y equals X squared.
Y equals X.
Y equals X, okay. And are we reflecting over the X or over the Y?
X.
Where's the minus?
Inside.
Inside. If the minus is inside, then we're essentially reflecting over the Y, which really doesn't. It does the same thing as reflecting over X. So really it turns our original parent the other way. I'll let you connect those dots. Write this down. This is reflected over X, and this is over Y. Okay, I'm not going to take the time to do the graphs, but I wonder if you can tell me the dilations in a couple minutes. Okay, when this was outside, we went over an example like this previously. When I gave you this and we said the number was outside, we did this example previously. Was this vertical stretch or vertical compression?
Stretch.
This was stretch, okay? When I moved the number inside, remember what inside refers to? Is that vertical or horizontal? Inside, horizontal, remember? So instead of vertical stretch, it's now called horizontal compression. It's got the same effect as vertical stretch. This is going to be called horizontal compression. I'm going to take you back. I just skimmed over it real fast for sake of time, but I provided all of this for you in your notes. See the difference between, go back to vertical stretch, numbers greater than 1, vertical compression, the numbers between 0 and 1, outside. And then if you want to do horizontal stretch or compression, you move the number inside. See some examples of horizontal stretch versus horizontal compression. Okay, I'm jumping around a little bit just to squeeze some problems in. Can somebody give me the equation for number 10? Kate, what do you think? Let's start with the parent.
It's y equals x squared.
Okay, and we took the parent, and the parent started here, and where did we go with it?
4.
Okay, and so the equation then would look like what? What do we do to this to show shifting up 4? How about that? Add 4? Okay, you got the assignment on the last slide. Do you have any questions? You can email me.